exactly is a function? So a function is a set of points that can be plotted on a number plane, or like a coordinate plane. You might want to change that to the word coordinate plane. However, there is a restriction, and there's an error on here, so please change this on yours. So it's saying here that no two x values can have the same y value. But remember, it's the wrong way around, because it's more like from the previous lesson. This one's not a function if an x value has if two y values share the same x value. So it is possible to be a function. You can have two x values sharing the same y value. That's fine. It's still a function. It's just a many to one function. But if two y values share the same x value, then it's not a function. So we need to change the notes here. So it should say no two y values. So let's change that now. So let's go no two y values can have the same x value. So if you want to do a little diagram of the previous pages of this, that's an example of something that's not a function, where two y values have the same x value. Then it's not a function. So hopefully we'll fix that up. So what exactly is a function? A function is a set of points that can be plotted on a coordinate plane. However, there's a restriction. No two y values can have the same x value. If it is, then that case, then it's still a relation. It's just not also a function. So which of the following are functions? So you've got to decide. Remember, we're following this. No two y values can have the same x value. So are there any y values that share the same x value in this one? Let's see. So the x values are negative 3, 5, 5, 3. So it looks like there is two coordinates that share the same x value. So see, two different y values in this case share the same x value. So in this case, it would be not a function. So let's type this in here. So not a function as two x values share the same y value. So not a function. So you might want to add that two x values share the same, two y values share the same x value in this example. Feel free to add that extra note in there, and it's all because of what's happened here. The next one, are there any two y values that share the same x value? So let's look at the x's, negative 6, 1, 6, negative 6. So and notice they're not the same coordinate. You might want to double check, are they just the exact same coordinate? Like, are they both negative 6, 1? No, they're not. It's negative 6, 1, negative 6, 8. So here's an example where two different y values share the same x value. So just like before, this one is same as before, not a function. Goodness. Not a function. For the same reasoning, that there's two y values that share the same x value. And the next one is, we've got 4 coordinates again. Is this one a function? Let's look at the x values. 4, 2, 7, 3. So they're all different x values, so it's not possible that two y values share the same x value in this one. So this one is a function. So let's type that in. Is a function. Fantastic. So it is a function in that case. Let's save that. If a graph is not a function, it is called a relation. So all of anything on plotted on a coordinate plane automatically is a relation. It's just there are certain relations that are also functions as well. So it's like relation is like the umbrella term, and function is kind of like a certain type of relation. So if it's not a function, it happens to be a relation anyway. But functions are also examples of relations. So by relation, we don't mean extended family, like in this kind of thing, so not like your relatives, but a graph where we can have two x values with the same y value. Hang on, is that correct? So this one is an example of a function. This one is example of not a function. So because remember, we can't have two y values that share the same x value. This is an example of the picture that I was showing at the beginning of this video on the previous pages. So this one's not a function because two different y values share the same x value. But this one is a function and it's a many-to-one function. It's possible for two x values to share the same y value. It's not possible for two y values to share the same x value for it to be a function. Both of these are relations. They're both examples of relations. That's why it says relation 1, relation number 2. But this one is a function. This one is not a function. But where a graph can, so by relation, where a graph can have two x values with the same y value. Grammatically, that's weird, I'm sorry. Okay, so the vertical line test is another way to test whether something's a function or not. It's a quicker way. So if it's been graphed for you, we can use a vertical line test to decide if it's a function. So when do you use this vertical line test? If you're given a graph rather than a set of points like on the previous page, and you need to find out if the graph is a function or is it just a relation. Is it a relation and a function, or is it just a relation? How does it work? This is important. If a vertical line cuts the graph more than once, so if a vertical line at any point can cut the graph more than once, then the graph is not a function. Some people by mistake think if it cuts more than once it is a function. A function is where a vertical line could only ever cut the graph once. If it cuts it more than once, then it's automatically not a function. If a vertical line cuts the graph exactly once, then the graph is a function. So here's a vertical line. So notice the function was a quadratic. So if you want, feel free to type in practicing what these things are. That's a quadratic function. Pretty color. Quadratic function. So it's a quadratic function. Here, any vertical line you draw will only ever cut this graph once. So it's not possible to draw a vertical line through this function and have it cut twice. So because notice it only cuts once. Where does it cut? This red vertical line only cuts there. But any vertical line you draw will only ever cut it once. So it is a function of x. Whereas this function, this kind of weird looking function here, like a sideways quadratic, a vertical line, it is possible for a vertical line to cut twice. You see, it can cut here, it can cut here. So therefore it is not a function. If you put a vertical line here, it will only cut it once, but it doesn't matter. It just means, is it possible anywhere on the function to draw a vertical line that it would cut twice, and then automatically it's not a function. So there might be some areas where it does only cut once, but that's not important. Is it possible somewhere on the function, on the graph, for it to cut twice? So that one's not a function. So we're going to use the vertical line tests on the next few pages to check out if the following graphs are functions or not. So I'll need my nice drawing line tools to draw some nice lines. So here's a quadratic again. Is it possible to draw a vertical line and have it ever cut twice? No. So see, you can do a few examples if you want. It never cuts. So use a vertical line test. Are they functions? Oops. Let's see. Is it a function? Yes. Or you can just put function if you want. If you want, feel free to also point out that it was a quadratic. Next one, kind of got a weird circle. Yeah, see, it's possible. If you did draw the vertical line here, it would cut just once. But we're not interested in that. We're just, is it possible for a vertical line to cut it twice? And this one, yes. So therefore, if it's yes, it can cut twice. It is not a function. What kind of graph is this one? Just practicing our types of graphs. That's right, it's a linear graph. Feel free to add that in if you want. It's a linear graph. Is it possible, a vertical line? Is it possible to draw a vertical line and it cuts more than once? No. If you drew it here, if you drew it here, if you drew it here, it would cut only once. So therefore this one is a function. Back to our vertical lines. This looks a bit like a sort of a weird half sideways parabola, or it could be a logarithmic graph, it's hard to see. Would a vertical line cut it more than once? No, it wouldn't. Vertical line could only ever cut it once, so it is a function. Feel free to pause and just try the next ones and the next pages by yourself, and then just check with my answers if you like. Otherwise you can listen along and do these ones with me. So here we've got the sideways kind of looking quadratic weird graph again. A vertical line can cut twice. Where can it cut? It can cut here and here. If you're not sure what I mean, it cuts twice. Cut here and here, a vertical line, same thing, that one would. This one could cut once, but so long as somewhere on the graph it can cut twice. So this one is not a function. And our next one, what kind of graph function was this one again? That's correct, it's a reciprocal function. Feel free to write that down, it's a reciprocal function. And it's got these little dot 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 asymptotes. A vertical asymptote here, part where the graph doesn't exist, and a horizontal asymptote here, because you can't divide by 0 in math. Remember, the reciprocal function in general is like 1 over x. Vertical line, would it ever cut more than once? Let's see, vertical line here would only cut once. Vertical line here would cut once. Vertical line here doesn't even touch the function, that's the asymptote, the part where it doesn't exist. So therefore, reciprocal function is a function. Let's keep rolling through this. So remember, back to here, like empty dots mean a part of the graph that doesn't exist. Filled in dots means a part of the graph that does exist. Back to vertical lines. What if you drew a vertical line through here? So that means technically, I'll undo this, it's not quite in the right spot. That means technically it didn't cut through, touch this part here because it's an empty dot, but it did cut the function here. So even if you did it through there, it still just cuts once. And the rest of it, obviously, it only ever cuts once through these parts. So it still is a function because this is empty, an empty dot, so this part does not include that dot. This part's a filled in dot, so this part does include the dot. So that vertical line only cut just right there. So if you want to, you're welcome to put in a little thing to say it just cut at that point. This one is a function, therefore, because it could only ever cut once through that graph. Some more examples. Ooh, crazy ones. So filled in dot, empty dot, filled in dot, empty dot. Are there any points where it would cut twice? Let's see, here, no, it would cut once. Here once, here once, here once, here once, here once, here once, here once. Because no matter where it is, it always seems to go through a filled in dot, but then an empty dot. And of course, in between, it would only ever cut once. So that one, that crazy looking thing, is still just a function. Function. Next one, some crazy looking things. Empty dot, filled in dot. These look like empty dots, but they're just coordinates, so ignore them. But this one's an empty dot and a filled in dot. Obviously a vertical line would only ever cut once through here. But if this was filled in and this was a filled in dot, then it would cut twice. It would cut here and here. But these one's an empty, one's a filled in, so it only ever cuts once. So this one is a function. See, are there any more on the next page? Oh, back to here. What is domain and range? Domain and range, remember, domain is where does the graph live vertically? Sorry, horizontally. What types of x values connect up with coordinates on the graph? And the range is how does it live vertically, horizontally, vertically. What y values? So domain is the x values for which a function exists, and the range is the y values for which a function exists. So what do we mean by domain and range? So examples, state what is the domain and the range. So I'll do the domain in green and the range in blue. So the domain, this is a parabola. You'll notice that it goes on infinitely this way and this way. So what are we doing? We're doing domain in green, aren't we? Domain in green. Domain, as you can see, if you spread out infinitely this way and this way, all values along the x-axis will correspond with the coordinate on the graph. So there's no values of x that don't correspond with a coordinate on the function, because it goes on infinitely upwards and infinitely upwards this way. So if that's the case, there's no x values where the function is not defined. You just say x is an element of real numbers, as opposed to writing out every single x value to say that yes, every single x part value will correspond with a coordinate on the graph. Just going x is an element of real numbers is a quick way to do that. Whereas the range of this graph, notice it's a quadratic. There's down here, so from here downwards, it doesn't exist. So the graph only exists from this point upwards. is where it exists, going on forever infinitely upwards. So we can say for y values greater than or equal to -2. See, the y coordinate of the vertex is at -2, and it's going upwards from there. So y values that are greater than or equal to -2. The next function is a linear function. They're easy. Linear functions, any value along the x-axis will correspond with a coordinate on the graph, because this graph goes on infinitely this way and this way. So any x value is going to correspond with a coordinate. They're the easiest ones to get, linear ones that go on infinitely, xer, and the range is just yer. So why is that? So any value of y will correspond with a value on the graph. Any negative value of y will connect up with a value on the graph and become part of a coordinate. So that linear ones are the easiest ones, xer, yer. Quadratics tend to be xer, but the y values are restricted because of the fact that it only ever goes upwards or it only ever goes downwards from a particular point. Next one, domain and range. What kind of function is this again? Have a think. That's right, it's a constant function. So would you agree any x value is going to correspond with a value on the graph? So xer for this one. Xer. But in terms of the range, there's only one particular point, y value, that corresponds with coordinates on the graph. So we can just say that the range is simply just this y value. Y equals, and what is that y value? So let's see, 1, 2, 3, seems to be 3.5. So it's not y is greater than or less than, because it's not any value between two y values. The only y value that connects up with the graph is y equals 3.5. So that's the case for a constant function. Feel free to write that this is a constant function in your notes. What kind of function is this one again? It's a quadratic. Feel free to write quadratic again. Quadratics are easy. Any x value, see this value is going to eventually correspond with a coordinate up here. Any value of x will correspond with a coordinate up here. So xer, easy peasy for quadratics, because it goes on infinitely upwards this way. Whereas the range sort of starts here and goes upward infinitely. So y values greater than or equal to, because it does include this point here, 0. Y values greater than or equal to 0. Some more down here. Domain, what kind of function is this? Have a think. That's correct, it's a cubic function. It goes on infinitely this way, infinitely that way. It might look like it's only from here to here horizontally, but it goes on infinitely this way, so it's going to continue spreading out that way and continue spreading out this way. So any value of x is going to correspond with the coordinate on this cubic function. xer. If there were no arrows stopping it here, as in like there was dots, if it specifically had in a filled in dot or an empty dot, that tells you it stops there. But this one doesn't tell you it stops, so it continues on infinitely. You might have guessed already that the range kind of goes from here upwards and from here downwards infinitely. So it's just yer for this one, because it goes upwards vertically, goes upwards infinitely, and goes downwards infinitely. What kind of function is this? Kind of looks a bit like a logarithmic function. Feel free to write that down. Seems to sort of start, it's kind of hard to tell, so we'll just have a vague estimate. Seems to sort of start at 0. So we can say x is greater than, it's hard to know, is it greater than or equal to 0? You would have to be given a better graph. So, because we don't even know for sure if it's logarithmic or not. So we can just say x is greater than or equal to 0. Y values seem to go up infinitely this way. So you probably can't see it, but it's meant to kind of like go down to there. So we can say y values greater than or equal to 0. In that case, it's sort of logarithmic, but it's hard to tell, so we won't necessarily write that down. What kind of function is this one again? That's right, it's a quadratic. Feel free to write down quadratic. Easy peasy for that domain, xer. Xer goes on infinitely this way and this way, but the range is restricted. It starts from here and only goes upwards. If it was a frowny kind of quadratic, it would start from here and go downwards. So y value is greater than or equal to -4, it seems to be. Y value is greater than or equal to -4. Now this kind of crazy function doesn't have a particular name, it's more like a mixed up kind of piecewise function. Assume that it's kind of going on infinitely this way. There's no dots to say it starts and ends here, so we can say that the domain is XER, but the range, it seems to be only between two values, doesn't it? Do you agree the range is only sort of from here to here? From here to here. So range values, we'd say between -1, so -1, the arrow should be facing to the left. It does include the -1 for y values. So y values between -1 and up to +1. So remember your arrow should be facing to the left. Y values between -1 and +1, and it does include those two values, which is why I put the equal sign on there. This one, domain and range, we've got some weird dots and stuff going on too. So it seems to be a mixed up domain. So we've got empty dots here, so maybe assume that it doesn't include those ones. So this seems to be, domain seems to be from here to here, and then up to about here. So two separate little domains. We can say x, we might have to write it like this. So -3, this way, doesn't include that point because it's an empty dot, up to 0. Because it doesn't include 0, we can't do it as just one long continuous domain. We have to write it as two separate ones. And then from 0 up to 3. And it doesn't include 0, doesn't include 3, doesn't include -3 because of the empty dots. So two parts of the domain. So you might want to put an AND in there or something like that to say that there's two separate areas to the domain. Range seems to be just as confusing. Oh no, range seems to go from here to here. Because even though that's an empty dot, there is this y value does coordinate with that point. So it seems to be from 1 up to 10. So 1, and it's y values, but they're empty dots on 1 and 10. So that's why we've kind of just got it drawn like that. From 1 to 10, empty dots. And that one, even though it's empty, does correspond with this part on the green graph. Same with that one, even though that's empty, there is a point that it corresponds with over here. And another crazy looking half quadratic kind of thing. So I've got empty dot, filled in dot, empty dot. Oh, well, actually think of that one as a coordinate if you want. So empty dot, filled in dot. So it seems to go from 0 to 2, the domain. So 0 to 2 doesn't include that one, doesn't include 2. And also from 2 up to 3. But it does include 3, would you agree, because it's got a filled in dot. So two areas of the domain. These are examples of much more complicated ones. So because there's two empty dots, it doesn't include 2. So that's why there's no equal to sign on the 2. And it doesn't include 0, but it does include 3. Range, let's see, seems to go from here. This one there is a point that it does correspond with, so it's fine. So from 0 up to 4. Doesn't, but it's empty on 0, it's empty dot on 4. So 0, don't forget to write y. Sometimes people by mistake write x in the range. 0 up to 4. Next one, it's a quadratic. Feel free to write that. XER, nice and fast. So XER, the range is y is greater than or equal to 0. And another quadratic, do you agree? XER, the range is y is greater than or equal to 2. Even though it's an empty dot, it's meant to be a filled in dot. Another quadratic, done overkill on the quadratics. XER, you kind of probably get these now, so that's why I'm doing them really quickly. Y coordinate, -4. So y is greater than or equal to -4. And notice they're all smiling, they're all opening upwards, so there were no less thans. A little trigonometric one, feel free to write that one down. It's going on infinitely horizontally, so XER, but the y values are only between 2 points. So y values from -1 to +1, and it does include those points. So y values up from between -1 and +1 for this trigonometric graph. Same thing, XER, it's going on infinitely horizontally. There's no dots to say it stops or begins at any point horizontally. The range values are between -3 and 3. So -3 includes those points, and +3. Sorry, that's meant to be +3. And another linear, they're easy peasy. There's no points to say it begins and ends, so XER. What is the range? That's right, it's YER. YER for linear. Constant function again, XER. Range is just 1 point only on the y, so y equals 2 is our range. Next one, domain, it's another constant function. The x value, only x value that's allowed is x equals 4, and the range is YER. Any y value corresponds with the point on the graph. YER. So sorry if this was overkill, but domain and range takes a while to get the hang of. So thank you very much.